Welcome to the latest update video on our hypersonic air-breathing engine called Aspire. The Aspire concept has evolved over several years of development, and if you aren't familiar with it, then I link a playlist of previous videos explaining the engine's development and operation as a card in the top right of this video. These other videos also contain links to our peer-reviewed papers. Very briefly, Aspire injects fuel from stationary injectors behind moving wedges to achieve a much better air-fuel mixing characteristic than is available in conventional systems. And good fuel mixing is considered critical to achieving a working practical engine. In an axisymmetric system, the wedges are situated on a rotating collar as shown in the animation on the screen. Behind each moving wedge is a dead space of stagnant air, which is shown in blue in this CFD simulation. The fuel is typically injected in discrete packages such as solid pellets, frozen solids, liquid drops, or gaseous capsules. As the wedges move past the fuel, it enters a main duct and mixes with the air. Our exciting news for this update is that we have now tried out the Aspire mixing system in a supersonic wind tunnel, and it works exactly as predicted. I'll show you some videos illustrating the operation. These were filmed at 240 frames a second in the wind tunnel with a Mach 1.75 approximately airflow. This corresponds to the flow in the mixing section of an engine which is traveling at about Mach 3.5. But actually the flow rate is much higher in our tunnel due to a higher fluid density. And so the pellets are having to overcome more resistance than they actually would in a real engine. In the first video, we can see a pellet emerging from the back of a wedge. Here is a still picture of the situation, and a video of it happening slowed down so that you can see it. I'll play this a second time in case you missed it. Now let's look at a zoomed out view of a similar event so that you can see the fuel dispersion better. The pellets used here were an organic starch, which was chosen because it mimicked the density and consistency of many cryogenic fuels. Here's a video which I think illustrates the process very well, this time using a water jet to mimic a liquid fuel. As you might imagine, we are very pleased with these tests, as they confirm that one of the key aspects of our system works much better than we dared hope. So where next? Well, we are currently working on a larger and better wind tunnel to do further testing, but our main emphasis is on a demonstrator involving a hybrid Aspire rocket engine called HyBi, which we will use as an intermediate step towards a full Aspire engine. I will link our peer-reviewed results when they become available in the description below. In the meantime, you might like to visit our website, which has full information on the development of the engine. There is a link to this in the description. On our website, you will also find a link to Change the World, or CTW, which is our project management tool and allows anyone interested to contribute theory, simulations, or experiments to the project. If you are interested in this, then please read the terms and conditions carefully first.